invitation. So, and apologies to everyone for the slight delay, about 5 minutes. I had some technical difficulties, which, after 3 years post-pandemic, I would have assumed that I know how to use my computers, but apparently it's not quite the case. But anyway, so my name is Turan Birol. I'm an associate professor here at the University of Minnesota. The department name is Department of Chemical Engineering and Material Science, though I have a physics background. And so I am here for telling you about some tools that might be useful in your first principles studies for solid state physics and material science. They won't be exactly first principles tools themselves, but they will be about some group theoretical approaches and some modern practical group theoretical tools that you can use to either support your first principles calculations or interpret your results. Okay, so let me give you a very brief overview of my research. So I'm a first principles theorist, and I use two computational approaches very commonly. First is density functional theory, which is essentially the workhorse of theoretical materials physics. And then there's dynamical mean field theory, which we use for correlated electronic systems. Now, in this workshop, I know there are other people talking about density functional theory, and there will be people like, say, Lucian Pascut, who was just here, or Christian Halle, who will give you an extensive introduction to dynamical mean field theory. So it's not what this talk is about. Instead, I'm going to tell you about this third method that I list here. It's the group and representation theory. So the group theory is a subfield of mathematics. And it turns out that, this was discovered in early 20th century, that group theory gives a very formal and a very powerful set of tools if you want to study the symmetry of a system. So this is why nowadays in physics, be it high energy physics, cosmology, or solid state or condensed matter physics, group theory methods and some tools are used very often. And this is what this talk will be about. It will be about the applications of group and related representation theories on solid state systems. I'm not going to give you a formal introduction to this area. This is not a math lecture. And really, actually, the introductory part of any group theory course is, in my opinion, extremely boring and tedious. It's like, it's like learning how an engine works and learning how to make an engine before you learn how to drive. So the aim of these two talks, I have one in the afternoon as well today, is to teach you how to drive rather than teach you how a car engine works. So we won't be extremely formal. Instead, I will wave my hands around a lot, and I will be giving you some hints here and there. And well, let's see how it works. Okay. So here is a brief overview of my talk. I'm going to start with a prelude about the symmetry of atoms and molecules, something you might have even seen in an undergraduate chemistry class, perhaps. Then I will talk about space groups a little bit. This might be something, if you have taken a solid state physics course, that you have seen there. But then I will talk about, for example, how these space groups determine the form of the macroscopic response tensors, like, say, compliance tensor or the piezoelectric tensor you can calculate from first principles. Then I will talk about vibrations of atoms in a solid, phonons. I will do a little bit of a derivation there, nothing too heavy. But then I will talk about how you can label them with representations of space groups, which enable you to study Chapter 5, the structural phase transitions. Finally, I have one case study in the end. There are these vanadium-based Kagome compounds that are extremely hot nowadays, and we have some research going on in my group about them as well. So time permitting, hopefully there will be some time to talk about them. I will be telling you about this cutting-edge application of group theory in combination with first principles density functional theory onto these Kagome compounds, and how they can enable you to understand the structural phase transitions in these compounds. Okay. So let's start with the symmetry in atoms and molecules. Now, let's imagine one of the simplest quantum mechanical systems we learn in undergrad, the Schrödinger equation for a single hydrogen atom. Now, the solutions of the Schrödinger equation we know are either in the form of spherical harmonics, or you can take the superpositions of spherical harmonics to get s orbitals, p orbitals, d orbitals, etc. And it turns out that we can classify all of these solutions in terms of their symmetry properties. So the hydrogen atom, even though we don't always discuss the symmetry in this context, carries a lot of symmetries. It carries the symmetry of any point in free space. So it is invariant under rotation around any arbitrary axis. So you can just draw an axis like this. And when you rotate the hydrogen atom by any angle around this axis, the equations remain invariant. So this is the SO3 rotational symmetry. And then there's spatial inversion, so the parity symmetry. So if you write down all your equations and then you replace the position r with minus r, nothing really changes. The solutions remain invariant. Well, the equations remain invariant to a good extent. So what this enables you to do is, when you write down the solutions and say s orbital looks like this, it's just a constant number, the angular part. This is invariant under all of these rotations and inversion. But then when you write the p orbitals, px, py, pz, which has these shapes, and you can expand them in terms of spherical harmonics too, these are orbitals that are odd under inversion. And when you apply these arbitrary rotations, it's interesting that these p orbitals transform to each other. So if you start with, let's say, px orbital, this one, and then you rotate your system around any axis by an arbitrary amount, what you end up with will always be a superposition of the three p orbitals. So it will not be anything that contains any part of, let's say, the d orbitals. And then the same applies to d orbitals within themselves. There are 5 d orbitals, and their shapes are a bit richer than the p orbitals. So it's harder to see it here intuitively. But again, these all are even under inversion. So they are still an inversion eigen state. And also, when you take any one of these d orbitals and rotate it by an arbitrary angle, you end up with a superposition of other d orbitals. So these d orbitals don't mix with p or s orbitals under inversion. So this all comes from the fact that there is an underlying symmetry of the Schrödinger equation for a hydrogen atom with the right potential, so that the solutions can be classified in this manner. Now, the symmetry also imposes selection rules. Because of this inversion symmetry and different inversion parity eigenvalues, which is -1 for p and +1 for the other orbitals, optical transitions, for example, are allowed between d and p and s orbitals, but you cannot have an optical transition. So you cannot have an electron fall down from a d orbital to an s orbital and emit a photon. So this is a selection rule that applies. And similarly, in external potential you apply, if it is inversion symmetric, it cannot mix p orbitals with s or d orbitals, so you cannot get off-diagonal matrix elements due to that perturbation Hamiltonian. But you can get off-diagonal matrix elements between s and d orbitals. So if you are into atomic physics, there are a lot of selection rules like this that essentially derive from the symmetry of the underlying problem. Now, atoms are nice, but they are spherically symmetric, a bit too simplistic perhaps. So while we are still in the prelude stage of this talk, let's move on to molecules, something slightly more complicated. So this is something, again, you might have seen in a chemistry class, perhaps because chemists work a lot with this type of symmetries. Let's consider, say, the methane molecule, CH4. It's a tetrahedral molecule, so you have the carbon atom in the center, and you have 4 hydrogen atoms forming an ideal tetrahedron, which is an object with 4 triangular faces. And this molecule doesn't have a continuous rotational symmetry like an atom, but it has various discrete rotational symmetries. So for example, if you take this atom and you look at it through one of these hydrogen-carbon bonds like this, then the angle between the 3 other bonds are all 120 degrees. So there is a threefold rotation axis that goes into the screen for the diagram on the left. So what I mean by this is, if you take this figure, leftmost one, and rotate it by 120 degrees around an axis coming out of the screen, the figure remains the same. There are more complicated symmetries for molecules as well. There's a 4-fold roto-inversion axis, for example. So if you take this vertical axis, you rotate the molecule by 90 degrees around an axis and then invert space. So take every position r to minus r. That's a fourfold rotoinversion symmetry that turns out to be present in this molecule. And additionally, there are a lot of mirror planes where, like, you, instead of a twofold rotation, you take the reflection of each atom on a plane that comes out of the screen like this. For example, the molecule remains invariant. Now, as I said, chemists work a lot with these symmetries of the molecules, these so-called point symmetries. Each of these symmetries I mentioned leave the atom in the center, carbon atom, stationary after all. So they actually came up with the language of a point group, which is a collection of all point symmetry operations, everything that I have listed to you, like rotations, mirror symmetries, reflection planes, rotoinversions, etc., that leave the system invariant. And it turns out that you can tabulate these point groups and you can give names to them. There are only a certain number that is relevant to us, really, and in solid state, actually, when in periodic systems, there are only 32 anyway. This is why we often refer to these point groups by name. This methane molecule has the point group T sub D, which we call -43M. So this -4 is how we sometimes typeset a 4 bar. So the number 4 with a bar overhead that denotes a fourfold rotoinversion. And this is a specific group. So if I tell you the chemical formula and then I tell you this point group, you can essentially build, in practice, in almost all cases, this crystal structure. So there are either tables, there used to be big tomes back in the day, now there are mostly web pages that I will talk more about in a bit anyway. There's, for example, this Bilbao crystallographic server, which allows you to learn the properties of these point groups. So if you check this Bilbao server, excuse me for a second, you can see the list of all properties, all symmetry operations that are included in this T sub D point group. It turns out that this point group has 24 symmetry operations, a lot of different rotation axes, etc. So I'm not going to go into details of that, but if you are into this, you can always find it.
There's a question in chat about.
Is there a chat? Give me 1 second.
So the question is, what was the D in the subscript of the point group name? By Bashli Mandal.
Okay, I need to know this. Sorry, I don't have it off the top of my head. So sorry for that.
No, but I can.
Do you know the answer?
I can help a bit. Yeah. So it's what you have there, what you explained to run with -43M. This is the physical representation. TD is the chemical representation of the same things. So chemists came with a much shorter version of the names. As physicists, we know the -43M.
Yeah.
But remember, OH, TD, these are the chemist notations, which I don't know exactly what it means. But if you look even on Wikipedia for the chemical notation of the point groups, there is a
exactly. So there are two main naming conventions. This 4 bar 3M, the one on the right, is the so-called Hermann Magen, I'm mispronouncing the name probably, but that notation that was developed by crystallographers. This is used more often in the solid state community, I think, especially people who do diffraction or first principles calculations. This T sub D is the so-called Schoenflies notation. So the chemists like this more. And also physicists who don't work as much with space groups, which will come later in the talk, but who just work with point groups, they also sometimes use this Schoenflies notation. So people like me or Luciana are more used to this Hermann Magen notation that as we said, I don't even remember this subscript's meaning. But good question, nevertheless. Okay, and if you have more questions in the future, yes, please type them in the chat. I will be checking the chat box from now on. Okay, now you might say, well, sure, each molecule has some symmetries, but why would we ever care about these? And really, the point of these two talks will be to give you some examples about what the symmetry information can tell you. A simple example that, again, chemists like looking into is the shapes and symmetry properties of the molecular orbitals. So when you solve the Schrödinger equation for the electrons on a methane molecule, and you can do this on a computer. If you do it in one particle level, perhaps you can do this at some basic level by hand as well. You are going to end up with some molecular orbitals. So the electrons' eigenstates will be some superpositions of the atomic orbitals in the system, which you can write also as some Cartesian function around the central atom. Now, there are these things called character tables, which I will not explain just yet, but they list all the forms of possible solutions of the Schrödinger equation. So in the case of this specific point group, here what I have is, forgetting about the characters, which is actually the main point of these tables, the central columns. The first column is the name of different representations. So each group comes with a group of representations. And the last column comes up with the examples of basis functions. So each solution of the Schrödinger equation for this molecule is going to correspond to a specific representation of the point group. If it is a one-dimensional representation with a single basis function, it will be a singly degenerate, so non-degenerate state. Or if it is, for example, a three-dimensional representation like this thing called T2, which has three basis functions that come in triplets, it's going to be a threefold degenerate solution of the Schrödinger equation. So you can use this type of information to guess what type of solutions you will get. You will not get the energy eigenvalues from group theory, but for example, by just looking at this table, I can tell you that, well, the highest dimensional representation is threefold degenerate. Therefore, whatever solution you get to your Schrödinger equation for methane, even though you have four different hydrogen molecule atoms there, you will end up with a threefold degenerate state at most. You will never get a fourfold degeneracy. So this type of information you can get without doing any calculation by just checking these point group tables for molecules. Other things you can do is you can also not just talk about the solutions of Schrödinger equation and the ground state properties, but also excitations. And as I said, I'm going to talk about phonons in detail in this presentation later on. So the equivalent of phonons in a molecule would be just molecular vibrations. So a simple molecule we can think of is carbon dioxide, which consists of one carbon atom and two oxygen atoms. This is a rod-like molecule, so they literally form a straight line. And you have three atoms. Here we are in a three-dimensional space. There are a number of rotational modes, and then there are a number of vibrational normal modes, which would be the solution of some like oscillator model you can build for this system. So the simplest way you would study the atomic vibrations in a molecule or a solid is you assume that there are some springs, and each atom has a different mass. The strength, the spring constant depends on the strength of the bond. And then you write down a matrix with all the atomic coordinates, and you solve for the eigenfunctions and values of that matrix to solve for essentially Newton's equation, right? Now, you can do this for a specific type of bonds between these atoms, but group theory, if you know how to do these, as we will by the end of the second lecture today, enables you to actually predict the forms of the vibration patterns. So it turns out that in the case of a molecule, a rod-like molecule with three atoms, where the two atoms on the edges are identical, there are only three normal modes. And whatever molecule you have with this shape, whatever the bond strengths are, these are the three vibrational modes you will get. The frequencies will be different, but the symmetry of the system imposes that you will have a symmetric stretching mode, where the two atoms on the edges vibrate back and forth out of phase, the asymmetric stretching mode, and the bending mode. And these, again, correspond to representations of the point group of the material, of the molecule here. So this fully symmetric one is called A1G. Again, this is just some name given. G is for even in German. It's a even mode because the two atoms on either end stretch evenly, like by equal but opposite amounts. There's this asymmetric stretching mode, which is a A1U mode. And then there's this twofold bending mode, the U1U mode. Now, group theory tells you that these modes exist, and it doesn't tell you the frequencies. For frequencies, you would need to do either a measurement or a first principles calculation. But what you can learn is that from group theory, the G modes, the even modes, A1G, for example, don't couple with external electric fields. And there isn't a deep physics behind it. If you think of external electric field, like the electric field of some like visible light has a long wavelength, right? So from the point of view of the molecule, it's just like a constant electric field, well, constant in space, so I'm a genius. Whatever the electric force that, say, the atom on the right feels under this vibration pattern, the one on the left will feel the opposite force, so their effect of the matrix element will essentially cancel, and so this A1G mode cannot absorb any photons, for example. But the U modes, the A1U modes or E1U modes, can interact with electric fields in first order, so they can absorb light, actually. And so they are, for example, called infrared active modes. So in solids, when you do an infrared absorption experiment, you see these modes being, you can see that at the frequencies corresponding to U modes, light is absorbed with very high intensity, whereas the G modes are not visible into that type of experiments. Now, this knowledge also turns out to be tangentially important, and this might actually end up ruining our lives, because it turns out that this E1U mode is really what gives rise to the greenhouse effects of the carbon dioxide molecules. So if this E1U mode was not interacting with light, actually, we would have much less of a global warming issue. But anyway, okay, so what can symmetry do for us? And when I say us, I mean the solid state physicists. I know here we have a very wide audience, and there are a lot of people who actually don't do solid states. But if you were to do solid state, this would also be applied to your work too. So we can use the space groups, which involves these point symmetry operations plus translational symmetry, to classify crystal structures. This is perhaps the most basic use of group theory in solid state. We can classify the solutions of Schrödinger equation, the possible electronic wave functions, according to their symmetry as well. And this applies not just solid state, but also to molecules or other systems as well. We can predict the form of these solutions even. So the like how many nodes there are, or whether the solutions are invariant under inversion, etc., without solving the Schrödinger equation at all. When it comes to excited states, apart from the electronic states, we can predict the forms of vibrational patterns, lattice vibrations, phonons, for example, in solids. And this we can do, this is the most important part, without actually performing any first principles calculations just yet. So this comes with zero computational expense, essentially. We can use all of these tools to verify the results of our first principles calculations, because, well, we tend to make, being human beings, mistakes in first principles calculations. Also, there's numerical noise that comes up now and then, right? So we can verify the results of first principles calculations or experimental observations using the symmetry principles, which are underlying our physical system. And finally, we can predict allowed coupling terms and allowed response terms to external stimuli of crystalline systems. Now, in this talk, I'm only going to focus on a subset of these. For example, I'm not going to tell you anything more about the electronic wave functions. There's a lot you can do, though. So I'm going to point out some online resources, and by just using these and reading a couple of textbooks, you can learn a lot more than what I will try describing you today. So these two websites I'm going to tell you about are the Bilbao Crystallographic Server, which is hosted in, well, Bilbao, Spain, as the name suggests, and the Isotropy Software Suite, which is hosted in the Brigham Young University in Utah, in the United States. Now, both of these websites are, they provide a set of group theoretical tools and tables that are extremely useful. In many ways, these tools or tables they provide are not original, in the sense that there are research papers, or in some cases textbooks, which has the same information. So in principle, if you know how to multiply matrices and you have access to a big library, you don't need these two websites. But what's really good about these two online tools, these two websites, is that they make things extremely practical. And the people who develop these websites are actually the cutting edge researchers in the area of applications of group theory. So if you just try to learn everything yourself without referring to these websites, you also come across the same names in the research papers. So they are extremely trustworthy, and to my experience, they are very well tested. In all my more than a decade in this profession, I think I found one mistake once in one of them, and I'm not even sure to this day whether it was their mistake or my mistake, but we resolved it after all. Okay, so without further ado, let me actually move on to space groups, some solid state system that you might actually be interested in doing a first principles calculation on. Okay, so I told you about point groups and point symmetry operations. So point symmetry operations include rotations, inversions, mirror planes, etc. In solid state, when you are working with a crystal, which is a self-repeating pattern of atoms that's in theory infinite, you also need something called a translational symmetry. Now, the translational invariance of free space is, the Galilean invariance is something that we know, and it's that, well, okay, if you perform an experiment on one corner of the lab, and then you take 2 steps to the right and perform the same experiment there, in the absence of any external effects, all the results of your experiments should be exactly identical. So that's a continuous translational symmetry. In the solid state, in these crystalline systems, we have discrete translation symmetry. So if this is a crystal, you can take a, okay, there we go. You can take a step to the right by one lattice parameter A, and the crystal is self-repeating and it's infinite technically. You will not be able to tell any difference. So each lattice site, each atom in a crystal on the corner of the unit cell is identical to each other. So this is what we call discrete translation symmetry. So this symmetry, when you combine it with the point group operations like rotations, inversions, etc., determine the symmetry of a crystalline system completely and uniquely. And it turns out that there are only 230 different ways to have a group of symmetry operations that describe a three-dimensional object. So in other words, there are only 230 three-dimensional space groups that can describe a crystal. And this was a result that was studied even before crystals were around, mathematicians working with things like this. Now, luckily, these space groups are also all tabulated. 230 is a large number, but it's a finite number, so people can work through these. Well, okay, before I refer to that, let me say that, again, for each crystal structure, you have a unique space group. So for a body-centered crystal structure, for example, the space group would be IM3 bar M. And there are numbers given to these. 229 is this number. For example, iron has this structure. For a face-centered cubic structure, you have FM3 bar M, number 225. Aluminum is like this. And if you have a compound like zinc blende, then you need more information than the space group. You need to know the internal coordinates of the atoms, of course. But still, you do have a unique space group. And in this case, it is F4 bar 3M, which is a type of face-centered cubic, but you can't quite see it obviously here, I guess. But it is given the number 216. And as I said, this is a finite number, so all the properties of these space groups are well tabulated. Now, if we were having this discussion, I guess, about 20, 30 years ago, I would probably be referring to these international tables for crystallography, which are published by the International Union of Crystallography. Each one of these are about 1,000 pages, and I think the libraries nowadays don't even buy the physical copies. There are PDFs of those available. But for practical purposes, if you don't like searching for things in 1,000-page tomes, essentially, you can use, for example, the Bilbao crystallography server that I mentioned before, which gives you a whole table of all the space group symbols. So here you have the names and the numbers assigned to them. and you can click on these and learn about the details of these space groups. So, for example, let's say that I have a material that is a space group with number 136, and I want to learn what type of symmetry operations there are that leave this crystal structure invariant. I can use this generators and general position tool and just type in 136 here, click on all general positions and click on the standard setting. And I end up with a list like this. So in this list, for example, the first row is the identity operation. If you are into the sites notation, something we discuss in condensed matter courses sometimes, identity is represented this way. And identity applied on a vector XYZ results in a vector XYZ, right? So it's this, here is a matrix form. Here I have a twofold rotation around the z-axis, 0, 0, 1 axis, which has this matrix representation and inverse the x and y coordinates of position, etc. So what you can always do is you can take your crystal structure. For example, if you are working on titanium dioxide with the rutile structure, it has this space group 136 P42/MnM, and you can find individual symmetry operations from the list that I just mentioned, and you can figure them out on your structure. So for example, this twofold rotation around the z-axis is this axis, shown in black here. So if you take the crystal and rotate it by 180 degrees around that axis, every atom moves on to another identical atom. So the structure is invariant. There is also this 2110. These are harder to see, but this is a in-plane twofold rotation axis around the 110 plane axis. And so it goes through this oxygen, titanium, oxygen bonds. And again, if you rotate the whole crystal by 180 degrees around this axis, again, the crystal remains invariant. So this is usually good if you have a slightly complicated crystal structure. And if you want to figure out, as we will do later on, what happens when there's a structural phase transition, how the atoms move, what new bonds are formed, etc., it's usually beneficial to dig a bit deeper to these sorts of structural features and understand the symmetry of the crystal structure. You can.
Duran, sorry, one question, if you don't mind.
Sure.
When you plot these things, have you done this manually, the axes or the planes, or you do them with some software? I mean, you can probably do it in Vesta, but is Bilbao crystallography server give you this option to just put the symmetry elements on the structure?
Unfortunately not. So these figures are from Vesta, but
yeah.
to manually draw these axes in the Vesta file.
Okay, thank you. Yeah.
So it would be, we tried to do it with one of my students, but well, he graduated and got a good job, so we never finished it on time. Unfortunately, to the best of my knowledge, there is no software which automatically imports the symmetry.
I want to do one here. That's why I asked with another student, and that's why I asked if somebody already did it or is still.
Nope. And, when you do it, please let me know as soon as possible. It would be a great and
it will help a lot to have manually, not will save some time for us. Thank you.
Yes, yeah. So I should say that like even if there was automatic tool, I think I would still ask my students, especially when they first start, to do this manually. So to like it gives the level of intuition that one can't otherwise develop.
I perfectly agree with you.
Yeah. Anyway, so these were the rotation axes. There are also mirror planes in this structure. For example, there's a 0, 0, 1 mirror plane, which just flips the z coordinate of each atom. That looks like this. There's a 1, 1, 0 mirror plane, and so on. So if you have your crystal structure right, and if you know the space group, then you should be able to reproduce every symmetry operation on this figure. And if I were to have an atom that doesn't obey the symmetries, just a single one of them, that would mean that I actually have the wrong structure. So this is a very pedantic way to check if you have the right crystal structure. Now, however, there are many space groups where there are tens of symmetry operations. And, as I said, this is a good exercise. I give it as a homework to starting students and so on. But life is short, and, you might not have enough time to check and confirm the space group of every crystal structure that you work with in your research. So is there a more practical and quick way to figure out the space group of a structure that we have? And the answer turns out to be yes. There's this tool called FindSim in the isotrope software suite, the other website that I mentioned that I will refer to often in this talk. And for any given crystal structure, it gives you the space group within, well, milliseconds. So if you imagine finding, how you would find the symmetry of a crystal structure, you would be looking for these rotation axes and mirror planes and so on, right? So this is tedious for a human being, but this is an ideal job for a computer which doesn't get tired, right? So there are only a few thousand possibilities of different axes after all. So as an example, I'm just going to show you a very quick example. Let's consider a VASP structure file. So VASP is one of these common DFT softwares. I have no affiliation with the developers of VASP. I just use it as I will use some input and output files from VASP in this talk just because it's one of the commonly used tools out there. So the VASP structure file consists of two main blocks, well, three main blocks, let's say. There's the first block, which is the lattice vectors. So these define the shape and size of your unit cell. Then you have a list of atoms. Say I have 1 barium, 1 tin, and 3 oxygen atoms. And then I have the coordinates of each atom. Here I have them in direct coordinates, so in reduced coordinates, which means that if I had zeros, if I have, let's say, the third row is 1/2, 1/2, 0, it means the Cartesian coordinate of the atom is 1/2 times the first lattice vector plus 1/2 times the second lattice vector. So this structure file is for the perovskite barium stenate. This is an interesting compound. It's structure-wise, it's a cubic perovskite, which is a rather rare thing, it turns out. But it has a very high electron mobility. It's a semiconductor that turns out to be both wide band gap and has high electron mobility. So it is of interest to people who are into that sort of applications. And so the thing about this structure file is that it has the cubic perovskite structure. It has the information about the structure with the space group PM3'221, but it does not have this information explicitly. So it doesn't say anything about the symmetry or the space group in this file, right? So most DFT codes, unfortunately, work like this. There are a few exceptions, say Win2K would be one, where the structure file includes the symmetry information as well. But most DFT codes don't rely on symmetry, at least at this input level, as much as they could. So let's see if this structure indeed has the right space group. So for this, we go to this FindSim. And one thing I should say before we move on to FindSim is that there's an extra issue with understanding the symmetry from the structure file. And it is that you don't, the structure you put in the VASP postcard file, this structure file, is not unique in the sense that these lattice vectors, for example, these clearly form a cube, right? The first one is along X, second one is along Y, third one is along Z, and they are all normal to each other. But I could have chosen a different set of lattice vectors to describe this exact same crystal structure. So for example, if you have a hexagonal lattice, as I've shown here, or triangular lattice, as we sometimes call it, this is one unit cell. So I could have chosen the two sides of this parallelogram as my two lattice vectors in 2D, but this is also a valid unit cell, and so is this. So this last one would have two formulae, so even the number of atoms would be different actually compared to the first two. But it's very hard for a DFT code to go through all of these possibilities and figuring out what the unit cell and shape is if you use the most sensible choice, right? Which would be a simple cube for a cubic structure. So this is when this FindSim becomes useful. So it's a web interface. So all of these tools I'm going to show you actually work in your browser. You can download some of them and run them. This FindSim, for example, also has a corresponding Python code that you can compile and run on the command line if you need to interface it with some other software you're using. But on the web, it has just a bunch of text boxes that you fill and you click on the submit button to get the results. So what we do is there is one text box for the lattice vectors. So there we essentially copy and paste the lattice vectors. There's one box for the types of atoms. So if we are talking about barium stenate, we have one barium, one tin, and 3 oxygen atoms. And then there's a third, 1 second, sorry. There's a third box here down on the bottom for the coordinates of each atom. And once you do that and click submit, you get a long output, and part of that output is this. So here I am, excuse me, okay. My pointer is not working for some reason. Okay, anyway, so here what you see is that there is the space group written 221. I'm having more technical issues today than I expected, for sure. Apologies for that. And oh yeah, here we are back. There's the space group number 221, which is PM3 bar M. So that tells us the symmetry of the system. And this is the type of check that I always do before every first principles calculation. So if I read the crystal structure from a paper, I try to reproduce it in my code. I check if my space group matches with what is reported, because if not, I must have a mistake somewhere in my coordinates. And below here are some other structural details. The most important detail after the space group, in my opinion, is the so-called Wyckoff position. So the positions of each atom in the unit cell can be labeled by a Wyckoff letter, which in the case of barium is A, tin it's B, and oxygen it's C. These Wyckoff letters are also tabulated in these international tables or the Bilbao server, and they tell you the positions of atoms in your unit cell. So for example, in the case of barium stenate, our space group is PM3 bar number 221, right? So in the Bilbao server, you can use a tool called Wyckoff, the Wyckoff positions, to translate these letters A, B, C into coordinates. So what this table tells me is that the Wyckoff letter A corresponds to the coordinate 0, 0, 0. Wyckoff letter B corresponds to 1/2, 1/2, 1/2. And Wyckoff letter C actually corresponds to 3 different positions, these 3. So oxygen, there are 3 oxygens in the unit cell, but still you have a single Wyckoff letter, which means that you have 3 oxygens here in these 3 different coordinates, which correspond to the 3 face centers of the cube. Now, this has 2 advantages. One, each Wyckoff site, for example, in the C, these 3 sites that share the same letter are symmetry equivalent. So, which means that these 3 oxygens are chemically identical, which means that if you were to calculate, for example, the projected densities of states onto these oxygens, you would get exactly the same number. And when you don't, it's just numerical error or you have a mistake somewhere else. So there are larger unit cells. Sometimes, for example, you might have a unit cell with like 20 atoms, 50 atoms in it, where you might have, for example, 10 oxygens, but not all oxygens share the same Wyckoff letter. In that case, you would have these oxygens have different densities of states. They would be chemically distinct. And this turns out to be important, especially when you talk about things like charge disproportionation or some sort of like mixed valence compounds and so on. You necessarily need this sort of separation in the Wyckoff letters. And the other good thing about this is an alternative way to store and communicate the crystal structure. So when you have this type of a crystal structure file where you have the coordinates of atoms and the lattice vectors, etc., this information is not unique because, as I said, there are different ways to choose the unit cell and so on. So when you have this structure and you want to compare it with someone else's structure, you actually might need to do some math. But when it comes to space groups and Wyckoff positions, this information is unique. So this is independent of the origin shift, for example. Well, there's a little asterisk there, but let's not get into the details. So instead of this crystal structure file, you can just tell me that the space group of berenstenate is PM3 bar M. Its lattice parameter is 4.134 angstroms, and these are the 3 occupied Wyckoff sites, and I would be able to reproduce that structure myself. Now, for a 5-atom unit cell like this might become a bit superfluous, like it's unnecessary, right? It's too much information. I need to refer to an extra table and so on. But once you move on to more complicated structures, this actually becomes extremely useful. So this is a very interesting compound. I like calling this crystal structure a monster because it has a very large unit cell. The primitive unit cell, the smallest repeat unit of the crystal, has 24 atoms in it. Even though the chemical formula is rather simple, like molybdenum 3, aluminum 2, carbon, determining the structure becomes tricky because you need this long list of 24 different atoms coordinates. Right? But it turns out that when you use the symmetry tools and the Wyckoff letters, this crystal structure is extremely easy to predict, to report. So referring to these tables, right, which are tabulated, standard, published, or available online, you can just say that, well, the space group of this molybdenum 3, aluminum 2, carbon is 213. So it's P4132. It has a lattice constant of 6.866 angstroms, and these are the 3 Wyckoff letters. So it turns out that even though you have 24 atoms in the unit cell, so if you just use brute force, you would need to list 24 sets of 3 coordinates for each atom. They only occupy 3 separate Wyckoff letters. So this crystal structure can be reported essentially in one sentence in a paper rather than this long list with all those weird numbers. Okay. Now, do we have any questions so far? Now,
Duran, I would like to make maybe a comment, or can you go back to the Wyckoff positions?
Yes. Which one? This one?
Yeah, here, for example. What I want to say is that I spent actually a few years trying to figure out what is the meaning if you just have a space group and a letter, let's say 1B or 3C, what's the meaning for each space group? Because if you go to various space groups, as you pointed out, you have various Wyckoff positions. Now, 3C, it doesn't mean anything. It's just a labeling. You cannot just say it's a 3C. You have to say the space group number and the 3C or 1B. And 3C can be, for example, here is 4 per mm.m, or can be something else. But Wyckoff notation has no meaning. I don't know why crystallographers picked it, but I spent a long time trying to understand the meaning, and in the end, I figured out there is no meaning to that.
Yeah.
To the Wyckoff, to the letters.
Yeah.
Just wanted to point that out for the students, so that they will not try to spend or waste time trying to figure out what's the meaning of these letters.
Oh yeah, well, very good point. I think so. There's very little meaning in the sense that if you look into the sites, symmetries and multiplicities, the lower letters are of lower multiplicity typically, and the site symmetry is higher. But other than that, I think the letters come in the order that Mr. Wyckoff picked. So like YC
yes.
come in this order and they are not swapped, for example. As far as I know, there's no logic either. Yeah. So
yeah, but I spent, I think, 2 years trying to figure out, reading a lot of papers, trying to go through just to see the meaning, and nothing.
Yeah, nothing. It's this is part of the these space groups and their applications, I guess. Like there are a lot of tables, and we refer to those tables very often. There might be some logic in the way that they were built, but nevertheless, that logic was not unique. And again, like I understand this A has a multiplicity of 1 and C has a multiplicity of 3, so A should come before C. But like, there's no reason why C should come before D, and the letters were not given the other way around. So these are not things that you need to memorize. And I, as a practitioner of this type of art, don't memorize these myself either. So this is just some common language, if you will. So these space group tables are like dictionaries, where we take the symbols from papers and translate them into coordinates and symmetry operations and so on. I teach a graduate course on related topics, and I get similar questions and sometimes even protests from students as well. And it's just that we need a consistent language, and this is what these tables provide. It's like, if you're a non-native speaker of English, there are quite a few things in English that don't make sense when you first learn it, but it's a natural language, so it's just how we communicate.
You're right, yes.
Okay, now a good number of first principle studies aim at reproducing some macroscopic response properties of materials. So these could be things like thermal expansion coefficients. These could be things like dielectric susceptibilities, perhaps piezoelectric tensors, and so on. So what we want to do is we want to perform this electronic structure calculation, understand the properties of this material, but then translate that result, perhaps through some post-processing, into some numbers that can be measured in the laboratory, right? And it turns out that some of those numbers and their relationships between them are also constrained by symmetry. And as a result, group theory can also help us actually predict the form of some of these macroscopic response properties, which are represented by tensors. And this way they can enable, for example, getting rid of some numerical noise or checking and confirming our results. So let me give you a couple of basic examples here. Things can get complicated fairly quickly here. So I thought about adding some more state-of-the-art cutting-edge research examples about some rank 4 tensors, etc. But I will keep things simple instead, because as I said, it just gets too many indices to keep track of fairly quickly. Okay, so when I say tensor is a fancy word, but a lot of the basic quantities that we learn even in high school are actual tensors, right? So for example, if we think of electrical conductivity. Now, conductivity, as we learn it in high school or introductory undergrad, is a number for isotropic material, right? You apply electric field in a material, you measure the current density, and there's a coefficient that connects down, sigma, that is a number. Now, in a crystal, however, different directions can have different meanings. Now, if you have a cubic crystal, if you apply electric field along X direction, there will be no current along the Y or Z directions. There will be a current only parallel to the direction that you apply the electric field to. And the ratio of that current density to the electric field, we denote as sigma XX. So the electric field along X, current measured along X. You can repeat the same experiment along the Z-axis, another axis of your cubic crystal, and you would get exactly the same number. So in a cubic crystal, the sigma XX is equal to sigma ZZ. Now, if you're careful here, I'm not just using a single sigma. I'm using a sigma with two indices because I can apply a current, I can apply electric field along a certain axis and then measure the current density along different axes. So this is already what we call a rank 2 tensor, which we would represent right down as a matrix. So conductivity in anisotropic media is a tensor, not just a number. Now, in a cubic system, this analysis don't make much sense because it doesn't give you an extra information. But for example, if you have a tetragonal system where, for example, the in-plane X and Y axes are identical, but the out-of-plane axis, the Z axis, is different because, say, the center atom in your cube has moved along that direction, then the conductivity that you measure by applying an electric field and then measuring the current density along X will be different from the conductivity that you measure by applying an electric field and then measuring the current density along Z. So sigma XX will be different from sigma ZZ. So space groups enable you to figure out what the form of this sigma tensor will be. So in general, we have this formula. So the current density is a vector. So the current flows in a certain direction with a magnitude. So it has three components. Those components are denoted by Ji, where I can be X, Y, Z. Electric field similarly is a vector. It has X, Y, Z components. And when you multiply the matrix sigma, the tensor, by the electric field, you end up with the vector J. And that multiplication, the matrix multiplying a vector, is represented this way, right? You sum over this common index. Now, the form of this matrix sigma is, as I said, determined by the symmetry. And space group is a unique determiner, but actually you don't even need the space group. Point group is more than enough for this, but space group determines the point group anyway, so I'm still talking about the space group in my talks. So if you have a cubic system, be it simple cubic, body-centered cubic, or face-centered cubic, the conductivity matrix always looks like this. So these dots are the elements that are zero by symmetry. So you cannot have off-diagonal conductivity in a cubic system. When you apply electric field along the x-axis in a cubic crystal, currents will be parallel to that electric field. It won't have a perpendicular component like a Hall effect. And then the XYZ directions are all equivalent, so the three diagonal elements of this matrix is equal to each other. In the tetragonal system that I just mentioned, well, the two in-plane components are equal, so sigma XX and sigma YY are equal to each other, but the out-of-plane component, sigma ZZ, is different. Now, if you have, for example, a monoclinic crystal, monoclinic crystals are crystals which I'm not sure if this figure is clear enough because it has this 3D perspective, but in cubic or tetragonal crystals, you have the three lattice vectors of your unit cell normal to each other. In the monoclinic systems, one of the lattice vectors is not normal to one other lattice vector, okay? So you have one angle that is different from 90 degrees. In these systems, you actually get these off-diagonal elements of your sigma tensor as well, because like it's possible to apply electric field along Z and get a current that is both parallel to Z, and that would be proportional to the sigma ZZ, but also there's a normal component which is proportional to the sigma XC. So the thing is, when you do a DFT calculation and you calculate the conductivity matrix, this tensor, you should always compare your space group, the form of the tensor it predicts, and what you get. Because in practice, often you will have some small non-zero numbers where you should actually have zero. Because, you know, for example, if you are calculating conductivity using something like, say there's that called Boltzmann, right? It's use a Boltzmann transport approach in combination with one-year functions and so on. Those are very hard calculations to converge because you need a very fine K-mesh. Sometimes when you switch to one-year functions, you accidentally break symmetries, etc. So this type of a check is always useful. Now, again, just as a summary, which elements of a tensor, like conductivity tensor, is non-zero, and which ones are equal to each other necessarily is determined by symmetry. These tensor forms, what I've just shown you, can be used to check the outcome of your calculations as I described. And by imposing these symmetries, for example, averaging elements that should be equal to each other or setting the elements to zero, which should be zero, they can reduce the numerical errors. Now, if you are curious about the form of a specific tensor that you will work with, you can use, again, this Bilbao crystallographic server. They have a tool called Tensor there at this link that you can use. And I know this is not a clickable link in the video, but if you Google Bilbao Tensor, you can find this page too. So it's as a simple web interface again. You first click on the select point or space group link. Let's say we pick P4MM, a tetragonal space group of that structure that I just showed you. Then you click on, so there are four groups of tensors. There are equilibrium tensors, optical tensors, etc. If you're interested in conductivity, you click on transport tensors. You select electrical conductivity. And here on the left, there is already some description of what this tensor is, and like there's a current density J proportional to sigma times E, etc. Anyway, there is a long list of tensors. So there are quite a few interesting tensors here, like all the magneto-optical ones are there. There are a lot of higher order susceptibilities that are here and so on. And now when you click get results, you end up with this page, which is really not surprising, right? So here you have sigma ij with I and j components. You have two independent coefficients. So xx, which they denote as 1, 1 here, is equal to 2, 2, which is 1, 1 again. And then there's a different sigma ZZ, which is sigma 3, 3. Okay, now with rank 2 tensors, this is not as big of a deal. You can guess the form of allowed of rank 2 tensors like conductivity without really learning much group theory. But there are a lot of properties, macroscopic properties, that require you to use higher rank tensors. So these are objects with not one index like a vector or two indices like a matrix, but these are objects with 3 or more indices. So, for example, an example that I personally like and that has a lot of technological importance too is piezoelectricity. So piezoelectricity is when you apply an electric field on a material and the shape and size of the material changes, or vice versa. So before we jump into piezoelectricity, let me mention strain. So strain is a change in the size and shape of the material. So if you change your lattice vectors by 1% in a particular way, that's what we would call a 1% strain. And strain itself is not a scalar or a vector, but it's a rank 2 tensor because there are many different ways to deform the unit cell. For example, if you have, this is a 2D example, but if you have a square, this is the zero strain state. So epsilon ij is equal to 0, no strain for any value of I or j. Now, if you elongate the cell along the x-axis, this is a normal strain component. This is what we would call epsilon xx. So this is the xx component of your matrix. But if you, instead of elongating the matrix along the direction, you shear it, so you deform it along one of the diagonals so that it's no longer a square or rectangle, then you have this off-diagonal strain components. This is called the shear strain. And since there are many different options to do this in 3 dimensions, you have more than 3 options for sure, right? Then you need a rank 2 tensor to represent strain. Now, piezoelectric effect, as I said, is when an applied electric field induces a strain in the material, or there's also the inverse effect too. So if you strain a material, if you deform a sample, if the crystal is piezoelectric, you would get a voltage form on it. Now, piezoelectricity itself is represented by a rank 3 tensor D. So a rank 3 tensor is an object, this D here, that has 3 indices. And the piezoelectric effect is represented by this equation. So if you apply an electric field, you multiply this rank 3 tensor with that vector of the electric field and end up with a rank 2 tensor that is your strain. So that multiplication between the rank 3 tensor and the rank 1 tensor, which is a vector, the electric field, is the summation where you sum the third component of the Dij tensor, okay, multiplied by the kth component of the electric field. Now, the problem is that, if you have a vector, it has 3 components. If you have something like conductivity, a rank 2 tensor, it's a 3 by 3 matrix. You can say, okay, at most it has 9 components, and typically it doesn't even have 9 independent components. For a rank 3 tensor, it's a 3 by 3 by 3 object, so you can, in the most general case, end up with 27 different components. So that's a lot of calculations, a lot of room for error, and well, a lot of numerical noise that might make it into your results. Now, luckily, it's slightly better than it seems because the underlying physical laws says that, well, the ijk component of D has to be equal to the jik component. So that allows you to get rid of some of the non-zero components by setting them equal to each other. But still, well, this rank 3 tensor has as many as 18 independent coefficients in it. So if you are going to do a DFT calculation and you don't know anything about symmetry, do you need to calculate all these 18 components separately? Now, the answer is no, and group theory allows you to reduce this number by quite a bit. And I should say before moving on that for something like piezoelectricity, which is, as I said, this is an effect that has tremendous technological importance, and it's very well studied. There are many DFT codes which does this calculation automatically. So if you're a practitioner of this sort of calculations, you might just say, well, okay, I don't need to think about any of this. The code takes care of it. But A, we need to know how the code works. B, we need to check our results. But C, also, every now and then you will face a tensor that you calculate that is not implemented in one of these DFT codes. So we really all need to learn how to impose these symmetry constraints on things that are not automatically calculated by our computer. Right? Okay, now I did a very quick calculation using the same code that I mentioned, VASP, and I intentionally did the calculation a bit low quality. So I used a small energy cutoff, not too many K points, etc., so that I get some more numerical noise than I typically would. The system I chose was tetragonal barium titanate. This is a very well-studied system, and it's a very well-behaved system. So it is possible to get very well converged results. Okay. So I'm saying this just in case, like if the developers of VASP sees this talk, don't get upset. I know your thoughts can do much better than this. Okay, so VASP automatically calculates using that functional perturbation theory the piezoelectric tensor. As I said, it has 18 independent elements because ijk is equal to jik. And in the output file, for example, this is the ionic contribution only. So this is the part that comes from the displacement of atoms. The result is reported like this. So the electric field is along the XYZ directions, the rows. And then the strain components, there are 6 of them that are given like this. And for example, the first component will be the XXX components of the D matrix. The last component would be the XZX component, which is equal to ZXX component. Okay, now when you look at this outcome, there are some numbers that are definitely 0, right? So there are some numbers that are actually written to be 0, but then there are some like this, which is what, 3 times 10 to the minus 5, which is 5 orders of magnitude smaller than some other components, right? These are probably just like numerical, residual, whatever from the calculation. So if I was writing a paper, I would set these to 0 pretty confidently. And then there are these are the worrisome ones. Like this is what, about 2 orders of magnitude smaller than the larger contributions, like say this component, but it is nevertheless 4 orders of magnitude larger than the smallest noise contributions. So I'm not sure if these would be 0, like this or this. So what I would do is I would check, what the form of the piezoelectric tensor should be using Bilbao crystallographic server, and see if these should be 0 or not. See how many independent components there are. For example, these two, in a tetragonal system, you can guess, but you have this term, which is 0.47277, and you have this term, which is 0.47284. These should probably be equal to each other, right? Yeah, but let's be sure. Let's check this, right? So when you do that check using the tensor tool, which also has the piezoelectric tensor there, this is the output you get. Now, this says there are 3 independent coefficients, so most components are 0, but the output is a bit more complicated than what we had before. For these rank 3 and higher rank tensors, the server uses something called the void notation, where, for the XX, YY, ZZ, XYY, ZX components, you have 1, 2, 3, 4, 5, 6. So instead of a 3-index tensor, this uses a 2-index tensor, where the first index takes care of all the strain components, for which you typically use 2 numbers. But anyway, when you translate this takes a slight bit of getting used to. So we can spend 10 minutes on describing this, but I will not. When you translate this into the normal people notation, not void notation, you end up with the fact that the 2 components XXZ and YYZ are equal to each other, which are these 2 components. So reporting these in a paper, you should symmetrize the result. You should take the average of them to reduce your error. The ZZZ component, this one, is non-zero by itself. And then these 4 components are equal to each other and are allowed to be non-zero. Now, these 4 components, actually, ZXX is equal to XZX, so not both of them are reported in the VASP output, it only reports 1. But the 2 components that correspond to these 4 numbers here is this one, so minus 0.0166, and this one, minus 0.0266. So it turns out that these 2 numbers are essentially not 0. These others are zero, so you can cross them out confidently. And these two are not only non-zero, but they should be equal to each other. So again, reporting this output in a paper, you should symmetrize this because the symmetry of your system says that these two should be equal to each other. And the only reason that these two are not equal to each other is that your DFT calculation did not respect the symmetry of the piezoelectric tensor. Now, different DFT implementations have different symmetry algorithms in them that detects part of the space group and point group symmetries that you have. They don't always go as far as they should. And this is why we should use these external tools like the Bilbao server to check those outputs and confirm them. As I said, things get more complicated as you go to higher rank tensors. For example, if you have a rank 4 tensor, you will have more elements that are allowed by symmetry and you will have more noise in your output. So using these tensor tools from group tier websites actually prove to be more useful then. Okay. Now, let's talk about phonons and the vibration, which are the vibrational normal modes of crystals. And this will allow us to talk about these representations of space groups, which I talked barely when I was talking about the vibrational patterns of molecules and the electronic states in the molecules early on. I think I have about 15 more minutes in this session, so I will try to give you a brief introduction here, but in the afternoon session, we will be back and I will continue from where I left off. Okay, now, again, in solids, you have these normal modes of vibration, which are the collective oscillations of atoms. Essentially, what you do is you build a simple spring model. You take the second derivative of the bond strength between each atoms, assign that as a force constant, and solve the resulting equations. Essentially, that's the Newton's law that you solve. These phonons are extremely important. They are partially, but in insulators, of course, to a larger extent, responsible of thermal and dielectric behavior. So the reason that you have thermal expansion or the reason that insulators can actually store any heat is that their atoms vibrate. Their frequencies and representations, so the patterns themselves, carry information about crystal structure and bonding. So there are many experiments, for example, Raman experiments, where you gather information about these vibrational patterns to figure out the properties of your solid. And sometimes you see, for example, structural symmetry breaking that is not visible in X-ray diffraction because it's very subtle, but it becomes more visible in these vibration patterns and their frequencies. The typical types of experiments people do to probe the phonons, these vibrational modes in solids, are infrared absorption. You shine light and see what frequencies are absorbed by phonons. Raman scattering, where you shine lights and some photons actually lose a specific amount of energy interacting with specific types of phonons. Or neutron scattering, where you shoot a bunch of neutrons to your crystal, and those neutrons excite phonons and lose some energy, and you gather what energy is lost at what wave vector and so on. Now, as I said, even though these are the scientific probes to study specific phonons in solids, many behavior, even as simple as thermal expansion, is determined by these phonons. So these are important properties, important excitations to study. And I'm not even getting into the optical properties and so on, which are also determined to some extent by phonons in specific limits. Okay, now let me do a little bit of derivation, maybe just like 10 minutes or so, to give you some mathematical background on phonons. So let's consider the simplest crystal that you can imagine, the monoatomic chain, where you have a one-dimensional universe, you have atoms repeating with a specific distance between them. So your unit cell is shown by dashed lines here. The position of the ith atom is denoted by x sub I. The force on the ith atom is the derivative of the total energy of this whole crystal with respect to xi. So this is the type of thing you can calculate in DFT because the total energy is calculated, right, solving the Schrödinger equation. And the derivative of that energy will give you the force. There's this Hellman-Feynman theorem, which does that without even using perturbations, like a without changing the wave function at all. This is the force on the atom I. Now, if in general you displace a bunch of atoms, so not just xi, but the x for many different atoms are non-zero, then you can write the total force on atom I as a sum with a minus sign of some force constant c, which multiplied by x of each different atom. So essentially what I do is, here what I'm doing is, I am Taylor expanding the force on atom I. So here I have the first derivative with respect to I, right? But then this first derivative I can Taylor expand in terms of another first derivative, which gives me a second derivative in terms of xj, and then sum over that j. Now, by solving the eigenvectors and values of this C matrix, I should be able to get the possible vibrational patterns, the normal modes of this system. So it turns out that since I have translational symmetry, those normal modes will correspond to these phonons with a well-defined wave vector. So I will have waves with well-defined wave vectors k, and for that specific phonon with k, this will be the position of the ith atom at time t. So k turns out to be 2 pi over lambda, as it usually does, and then there's a specific value of omega for which I need to solve the Newton's law to figure out omega as a function of k. So when you plug this form, this ansatz, let's say, if you don't believe that it's the solution, let's call it an ansatz and see if it really solves something. When you plug this solution into Newton's second law by taking the time derivatives, so the time derivative just brings the t in front of the exponential and so on, and you end up with the expression like this for omega. And if you consider the simplest case where the c is non-zero for only nearest neighbors, so when you displace an atom, only its first neighbors feel a force, but the next neighbors don't feel any force, then you end up with this form of omega, which is a simple square root of 1 minus cosine function. And this is what you get for omega as a function of k. Okay, so this is what we call a phonon dispersion. And in every solid, you have some phonons. In real life, of course, the phonon dispersions are much more complicated than this. So the reason is twofold. One, you have a three-dimensional system. So atoms can be displaced not only along x direction, but also y and z direction. So you have 3 phonon branches. And B, typically you have more than one atom in your unit cell. So for example, if you have 2 atoms in your unit cell, a black atom and a red atom, then the indices become a bit trickier, right? Because you need to have a unit cell index, which I denote by R, and an atom index, which I denote by I. Then the C matrix becomes a larger matrix because you have to have the force constant between the 2 atoms in the unit cell and the 2 types of atoms in the neighboring unit cells and so on. But long story short, you can still plug things into the Newton's second law. You still end up with a similar equation, similar ansatz for the phonons. And in the end, you, for example, in this case, one-dimensional diatomic chain, you end up with a different branch for each atom. Now, the 2 branches here are referred to as acoustic and optical branch. The acoustic branch is when the 2 atoms in the unit cell, the red and black, move in phase. And the optical branches is when the 2 atoms in the same unit cell move out of phase, move against each other. Therefore, the frequency is higher. And in the end, the equation you solve is the eigenvalue equation for this, where y is some reduced position coordinates. And this matrix here is what people refer to as the dynamical matrix. It's Dij. So the frequencies of the phonons, or frequency squared, omega squared, are the eigenvalues of this dynamical matrix. And the dynamical matrix is nothing other than the second derivative of energy, which is the force constant matrix C, divided by the square root of the masses of the 2 atoms. So again, the phonon frequency squared is the dynamical matrix eigenvalue, and the dynamical matrix is the force constant matrix, the second derivative of energy, divided by some mass factors. Here I want to underline that people sometimes colloquially refer to D as the force constant matrix or C as the dynamical matrix as well. So that I think gets pretty confusing pretty quickly. So I will distinctly refer to D as the dynamical matrix because it has the mass factors in it as well. Okay, now in DFT calculation, and DFT is now perhaps the most common way to gain information about the full Phonon spectrum of materials, because Raman and infrared absorption experiments are only valid for a small group of phonons, only at the gamma point, zero wavelength vector phonons. And the neutron experiments are extremely expensive. It turns out that you need a nuclear reactor to do those, but DFT is relatively cheap. So DFT is very commonly used to predict the phononic properties of materials. So in typical DFT calculations, we work with small unit cells, right? We work with the primitive, the smallest unit cell when possible, and use periodic boundary conditions. Now, this makes it hard to get real space force constants. So when you displace a single atom and want to figure out what the force on another individual atom far away is, that's what I call a real space force constant. So what we do in DFT instead is we work in the reciprocal space with phonons of well-defined wavelengths. So for example, I take this unit cell and I displace this atom, but as I have periodic boundary conditions, every other equivalent atom in the units, in all the unit cells in the infinite crystal is displaced as well. So that would be a typical DFT calculation I make. And that gives me the phonon with a specific wavelength instead of the force constant of a single atom. Then I can take the force constants from reciprocal space with this well-defined wavelength and take their Fourier transforms to obtain real space force constants if need be, to find the individual force between like this atom and some other atom. And when it comes to calculating this Dij, which is the dynamical matrix, since the atomic masses are known, you only need to calculate the Cij, the force constant matrix from density functional theory. So the Hellman-Feynman theorem allows you to calculate forces on atoms for a specific configuration. So you can displace each atom one by one along XYZ separately and get the force constants, theCijs. Or you can do density functional perturbation theory to do the same. Density functional perturbation theory is now implemented in pretty much any commonly used code that gives you the force constants for like all the atomic displacements if need be, plus more, like it can give you the things like response to external fields and so on. These all work well at the zero wave vector limits, which would be like this, where all atoms, all equivalent atoms in the whole crystal move in phase. When you have a finite wavelength, so that some atoms in neighboring unit cells don't move in phase, you either need to build a supercell. So you need to work not with, say, in the previous case, not with two atoms, one red, one black, but you need to build a supercell with 4 atoms, 8 atoms, etc. And that's what PhonoPy does, essentially. If you are into using PhonoPy, that's one of those commonly used phonon calculation tools nowadays that interfaces with most DFT codes. But you can also do DFPT at finite wave vector. This is a bit tricky to implement in POE, projected augmented waves, I believe. So this is why, for example, the VASP doesn't actually support DFPT at finite wavelengths. It only does that 0K. But other codes like Espresso or Ebinet has this implementation. So they allow you to calculate the phonon dispersion throughout the Brillouin zone. But in either case, and especially when you use these supercell approaches like PhonoPy, you might need to be a bit careful because the noise goes up. And also when building these supercells, if symmetry is not taken into account properly, you might end up with splittings, for example, that should not be really there. Okay, now what I will do is, when we come back in the afternoon, I'm going to, by starting from barium stenate, the nice cubic perovskite, tell you what group theory tells us about the phonons. In particular, I will show you that group theory assigns a representation, a label to each vibrational mode, each phonon mode of a crystal structure. And this way it allows us to A, figure out the degeneracies of these phonon modes, and B, say something about the displacement patterns. And by using these displacement patterns and the representation labels, we can also say things like, oh, this phonon is Raman active, therefore it will be visible in a Raman scattering experiment, versus, oh, this phonon is infrared active, therefore it will absorb light in a resonant fashion even. So yeah, but this will require a deeper dive, and we are unfortunately out of time. So for now, I want to thank you very much for your attention, and if you have any questions, I will be happy to get some.
Great, thank you so much, Dr. Birol.